is titled Tasks for U4L18. And the first thing we're going to do is a Google form do now. This is not graded. You're going to be using this orbit simulator. It's pretty simple. There's a little control panel here on the right that you'll have instructions on how to use it. And then just answer these questions. I think there's a couple multiple choice. Oops, that's the wrong do now. That's our next one. But just answer the do now questions, and we'll check in about 8 minutes. Let me know if something doesn't work, if you have questions. All right, kiddos, 8 minutes has elapsed. Looks like we've got 12 responses, 13 in the class. That's good. Let's come back together, take a look. What'd you think? Pretty simple simulator, kind of fun. You can actually do a lot more with it. So if you guys want to play with it, you can actually, that little blue arrow that's on the moon, you can adjust that. So the bigger the arrow, the faster the initial launch. You can also grab the moon and drag it to any location you want. I didn't do anything with that, but it's actually fancier than it looks, that simulation. But questions look like they were pretty good. So when you first animated it, you should have seen something like this. What kind of orbit is that?
Circular.
Circular. Now I know it is a little confusing because I know some of you were like, wait, I thought the moon has an elliptical orbit. The moon technically does have a slightly elliptical orbit, but this simulation starts off, kept it simple, looks like it's circular. So then it makes sense that when we increase the mass of the planet, the moon gets pulled in, because what did we learn about the relationship between mass and gravitational force?
Directly proportionate.
Yep, so you increase one, you increase the other, and I think that's what pulls the moon in just a little bit. Then you had to, what was the next part of that simulation? Now I'm forgetting the next question right after reviewing it, but yeah, it looks like you were good there. Oh, and then we drastically increased the weight of the planet. So then what type of orbit did it fall into?
Elliptical.
The elliptical orbit, right? Which again is kind of an ugly one. And what did you notice about the speed of the elliptical orbit? What did it do?
Increase.
Yeah, right. It got really fast where?
Near the planet.
Right next.
Yeah, so it kind of hooked around and then it slowed down and then came back in. And I like that because I think it really drives home that point that elliptical orbits alter the speed of the orbit, and it's a lot faster when it's closer to the body of gravity, which makes sense. And in reality, there's another focus point right there out in space. There's nothing there, but that's the other sort of, that's the elliptical focus point for, you know, you could measure the ellipse and draw it, do all that stuff. So anyway, and then when we drastically decrease the mass of the planet, what did the moon do?
Sort of.
Mm-hmm.
Yeah, right. So anyone tell me what velocity it managed to achieve?
Yeah,
Technically escape velocity, right? Because we've completely eliminated the gravitational pull that was occurring between the planet and the moon. That's all gone. And so now the moon can literally just, there's nothing holding it there, and it just shoots off. So, all right, good. Most of your responses look really good on that. Any questions or comments? Okay, our main activity today in class is going to be to use a slightly fancier simulator from PhET to explore orbit in a little more detail. This was kind of a warm-up and reminder. Before we move on to that, though, I wanted to give you a chance to ask questions about the homework, which was the reading check questions from chapter 28. I think these were on page, I don't remember the page number, 840 something, right?
Let me see.
I think the questions were on 849.
849, all right, here we go. All right, any questions on 1, 3, 5, 7, or 9? Anything you had trouble with?
Can you go into more detail about like sunspots? Like I was able to find a little bit about it, but like a little bit more.
Yeah, it's something I wasn't that familiar with either, so it's kind of cool. It turns out the sun, anyone know what state of matter the sun actually is? Is it solid, liquid, or gas?
Liquid.
It's actually a liquid, which is kind of weird to think. And so if a liquid is orbiting, it turns out that the middle of the sun rotates a lot faster than the top or the bottom, right? Because it's liquid. So it's sort of It's not an even orbit like you would see on a solid planet. And so that's sort of almost, if you think about like the way air moves on Earth and what we learned about tornadoes and hurricanes forming, it forms these sort of eddies, right? That's the best way I could describe it, is you get these sort of like magnetic zones is what they call them, right? Where it's cooled down, where motion and fusion, and the book is hilarious. It's like, oh, it's relatively cool. It's 4,000 Kelvin, which is still unimaginably high temperature, but relative to the rest of what's going on with the sun, those are what we call those dark spots. That's where it's cooled down enough that I guess you don't have that extreme light coloration. So to put it in simple terms, it's because of the liquid orbit of the sun creates these sort of magnetic dead zones, almost is what you could call it, where things cool down. I don't know if that helps, Kenson, but that's kind of the main thing behind it, is it's just an uneven orbit because of the liquid nature of the star. It's a good question.
So does that mean like the sunspots like appear more in the equator, or?
I don't know much about their location, but I do know that what's interesting is that for some reason it's every 22 years. It's like a cycle. So it takes about 11 years. Sunspots sort of build up on an 11-year cycle. Like that's what, like, you can kind of tell where the sun is in its phases, because it'll develop a whole lot of sunspots, and then they'll all go away, and then they'll come back again. And it seems to happen. It takes about 11 years for them to form, and then 11 years for them to fade. At least that's what the book seemed to say. And so it wouldn't surprise me, though, if we do see more at whatever the equator of the sun is. I don't know where the equator of the sun is or how the sun's rotating relative to the rest of the planets. But yeah, it wouldn't surprise me if we would see more there, because that's where you're seeing that unequal rotation. So that's a good point. Which question was that in relation to? Number 7. Everyone feeling okay on number 5 with the whole nebula theory thing? I feel like the chapter wasn't very clear on that. What do you think? Did the planets form before or after did they start to form before or after the sun ignited?
After.
Before, right?
Yeah, so the chapter makes it really confusing, because they started the chapter off saying everything formed at the same time and blah, blah, blah. Anyway, yes, the planets started to form before the sun ignited, right? It is before. Because technically everything started at once. The sun hadn't actually ignited. It didn't have enough mass to really start the fusion reactions. And then as everything was beginning to form and bang together more, the sun got massive enough to ignite these fusion reactions, which are still going on. And even though the planets had already started forming. So yeah, so technically the correct answer is before. All right. Any other questions on that? Okay, then we'll move on to the main activity, which is 2 things you're going to be doing. You'll be using, this is task number 3 right here, Gravity and Orbits PhET. Open up the PhET simulator. It'll give you 2 options, model and 2-scale. And I encourage you to play around with the 2-scale one, but we're going to start with model. And it'll open up this. It's a fancier version of what you were using on the Do Now. You can see you've got a lot more controls here and settings that you can change. We're going to be using 2 different ones. The first one is this third one down. Click on that right there, and it gives you the Earth and the Moon. That's what you'll start off using. And then once you've answered a few questions on that, you'll go one more up, the second one down, where you've got the Sun, the Earth, and the Moon. There is a Canvas quiz. The link to it is also there with number 3. It's 4 multiple choice questions and then 1 free response question, which is actually a Flipgrid. So this is something new I want to try, where I want you to post a Flipgrid, but post a screen recording. And you can do this by, when you're ready to hit record, like you're ready to record a video, right next to the record button on Flipgrid, there's sort of 3 dots, that kind of more options symbol. And one of the options is screen capture. It's a beta program that they're running. So it might not work for everybody. If it doesn't, that's okay. Just you can use QuickTime, if you've got QuickTime on your computer, to film your screen. If you've got a Mac that's running Mojave or later, if you hit Command-Shift-5, it'll pull up a little automatic screen recording option on a Mac, which just saves it right to your desktop. It's super easy. But that's what I'd like you to upload to Flipgrid. I'll be here listening if you have any trouble with getting this to work. I put instructions right there on the Canvas post too. There's literally videos on I made a short video on how to use the simulator if you want to watch that. I made a short video on how to record your screen using Flipgrid. But again, if you have trouble, you can just send me a screen capture as well of your screen or whatever it is that you need to do. But I'll give you the next 20 minutes to work on task number 3. And I'll be here listening if you have any questions or need help on anything. So any questions before we start? All right, 20 minutes to complete that, and then we'll check back in. Go for it, and just let me know. Again, I'll be here if you need help with anything. All right, kiddos, 20 minutes has elapsed. Let's come back together. Even if you're not done, it's okay. This can just roll into homework. You can save it to do later or just continue working on it once I let you go on the next task. What do you think of this simulator? You're all getting sick of PhET simulators? Nadia's not nodding. Do you use them in other classes, or am I the only one using them?
You're
What,
the
the
only
PhET
one
simulator?
using it, but we use the same ones like for every lesson during.
No, I know that I beat that the projectile one to death, so I apologize for that, but it was a good review. I'll try to change them up a little bit more. But yeah, I like this one. It shows you some more fancy details. And looking over your responses, looks like most of you are feeling good. So how long does it take the moon to make a full circle?
Like 27 days.
Mm-hmm. And does anyone know how we refer to that? There are 12 of them in a year. Anyone know what we call a cycle of the moon in our calendar? Again, there's 12 of them in a year, 12 rotations in a year. We call them the...
Just tell Elizabeth so she knows that you're different.
Mm.
Come on, show me your face, quick.
Come on, what are there 12 of in a year? What makes up the whole year?
Months.
Months, very good. A month is based on a lunar cycle, basically. It's not exactly perfect. We've done some adjustments due to our calendar, but yeah, those are the months of the year. In fact, it is currently a very special month. Islam is a religion that is very moon focused, right? The moon is one of their main symbols. A lot of that religion is based on lunar cycles and behaviors of the moon. Does anyone know what special month it is for followers of Islam, for Muslims?
Ramadan.
I know they fast this time of year, but
Yep, it's Ramadan. So for one full lunar cycle, so for a whole month from no moon all the way to full moon, and then the moon has to go again and reappear. For that entire month, they do not eat or drink anything while the sun is up. It's one of the 5 pillars of Islam. It's meant to sort of help them sympathize with the poor and people who aren't able to eat food. So they're basically starving during the day. But yeah, for a whole month. And so, again, I lived with a Muslim family for years when I was in the Peace Corps. And it was funny seeing the different way that people reacted to this at the end, because normally they broadcast a radio announcement like, oh, okay, we've seen the moon, so you can stop your fasting. Ramadan's over, and they have a big party. But some people actually hold out until they have seen the moon. And so my family was like that they, even if the radio announced it was over, they would all go outside and they would be looking at the night sky because they had to see the moon before they would let themselves stop fasting. So anyway, pretty incredible practice of faith, if you ask me, but is all based on the moon and that 27-day cycle. So next question, a lot of you seem fine on that. Earth's I like this added detail that Earth actually does a little tiny circle. And I don't know if you noticed this, but everyone got it. That the Earth actually rotates a little bit on its own orbit in response to the moon rotating around it, even though the masses are pretty drastically different. But yeah, not surprising, if you turn off gravity, the moon just flies off on its tangential velocity. There's no gravitational pull. And technically, if you turned off gravity, the Earth would also be shooting off away from the sun. That would not be, it'd be like releasing marbles at random. What I really liked about this simulation was the detail about the moon when you are seeing it rotating around Earth while Earth rotates around the sun. And I think it kind of clarifies that when you finally take that into consideration, when you're seeing moon, sun, and Earth, the moon actually doesn't have a constant velocity around the Earth, right? It sort of looks like it's getting dragged along. Did anyone hit when you hit the line, the drag line that they show, kind of looks like a flower, doesn't it? The moon was almost making these little jumps around Earth. And anyway, I think that's kind of a really interesting pattern to see, that in reality, the moon is sort of slingshotting around the back of Earth and then slowing down as it cuts in front of Earth, and Earth passes it, and then it slingshots around again. So it's a little more complicated than sort of just saying that the moon has a tangential velocity and it just maintains it the whole time. There's actually a little bit more going on there, and I think that explains some of the dynamics we see with eclipses and all that kind of stuff. So interesting stuff there. And then the Flipgrid, were most people able to screen capture and post? Again, if not, it's okay to email me or just let me know if you need help or you're not sure how to do it. But it's my first time using it. It seems like it went well in this class and my other classes too. So, all right, any other questions or concerns about that or about the orbit simulator stuff? Okay, so for our activity today, yeah.
I did mine, but it has like voices in the background, and I'm trying to mute it. Is there a way to mute on Flipgrid?
There might be. I haven't explored that. I mean, I'm okay with it. I'm not going to listen. I usually watch them once and I just grade it. So you don't need to worry about it. But yeah, there might be. I would explore that and see if there's a way to cut off the audio or even maybe to tell your computer to not give the program permission to access your microphone. That might be the best thing, is just turn off your microphone on your computer, and then that might work. So,
thank you.
All right, so the next task that we're going to do is just a short lesson. The activity for today, which we'll probably roll into homework just because we're going to be short on time. But I want you guys to draw some orbits, specifically a circular orbit and an elliptical orbit. And so the elliptical orbit's going to be a little bit tricky. But basically, you're going to need a sheet of paper, printer paper, and I'm going to use a board just to demonstrate. But the way that we're going to start by putting a dot in the middle, which will be our star. And the way to draw an elliptical orbit is you want to actually make 2 points, right? So I've made one darker because that's our star, but then the other point, and then you can kind of draw a little elliptical shape around that. So we'll be drawing this and then doing some math around it. Specifically, what I'm going to ask you to describe for me is called the eccentricity. The eccentricity of an ellipse. And what that means, in short, is basically how circular is your ellipse. Circles have an eccentricity of 0. So a circle equals 0. And so the closer to 0 your eccentricity is, that means that you have a very circular ellipse. And if it's a long way from 0, you have a very elliptical ellipse, right? A much wider one. And eccentricity is calculated by doing what's called C over A. It's just a fraction. You're just dividing 2 numbers, C and A, and I'll describe what these are. But it should end up being a small number divided by a big number, because you're going to get 0 point something. So the first thing you're going to need to do is find the center of your ellipse. Does anyone know what would be an easy way to find the center of my ellipse? If I drew it based on these 2 dots, and I know my drawing isn't very good, but everything should be evenly distributed, what would be the easiest way to find the center of an ellipse? What could I measure?
The distance between the moon and the Earth.
Well, I mean, not thinking about, this is just basic geometry, right? I like you're thinking about planets, because yes, we're going to talk about moon and Earth and elliptical stuff. But right now, just for math with ellipses and shapes, if you've got 2 dots, the 2 what are called the foci, which I know I had the star and another one here. All you want to do is measure the distance between them and then divide by what?
2.
Divide by 2, and that gives you that center mass, right? The halfway point. That is technically the center of your ellipse, okay? And then the 2 values here, the C value and the A value, the small value, C, is just the distance from the center to one of your dots. Doesn't matter which one of the foci, that's your C value. And your A value is the distance from the center to the outermost point. So again, you're doing a small number divided by a big number, or again, the distance from center to one of the foci divided by the distance from the center to the outermost point of the ellipse. And I've got a video explaining this. I have written instructions explaining this. So just give it a try. It's pretty straightforward math once you know what to measure. And you'll just need a ruler, or you can use the Measure app on your phone. Works super well as well. Now, a circle is much easier. Most of you, I think, are familiar with basic geometry, so you'll also draw a circle. And what I'm going to ask you to calculate for the circle is the circumference. Does anyone know what a circumference of a circle is?
2 pi r.
Very good. And what do I mean by circumference? So when you're calculating 2 pi r, what are you actually calculating?
It's the outermost, like the perimeter of it.
Bingo, right? If I took that circular line and I straightened it out, how long would it be? right? That's the distance all the way around. So yeah, and that's 2 pi r. Is anyone familiar with the value of pi?
3.1415.
Yeah, so just use 3.14 for me. 3 sig figs is fine. So, all right. So you're just going to be doing that and then drawing something that should come out looking something like this, where you'll have a circular orbit and elliptical orbit. I'll have you name your planets whatever you want, and you'll do a little bit of calculations for that. On the Canvas post, I have all the instructions written down there. So if you look, this is task number 5, I believe. Activity. Right below that, I have a video demonstrating how to do this. I have the instructions all written out, so do it however you want to do it. If you want to read the instructions, if you want to watch the video and follow along, that's fine. But I'll give you, you're going to need pins and some floss or string to get drawing on your ellipse. For time, let's take about, I want to come back here at 11:55. So I know that's not very much time, but it's at least something that you can get started on it, and I'll let you finish for homework. So that gives us probably about seven minutes to at least work a little bit on this, and then we'll come back together to wrap things up. And again, let me know if you need help on anything, but I would just start watching the video, reading over the instructions. All right, kiddos, I know that wasn't very much time, but let's just come back together to touch base, wrap things up. Most of you able to find some kind of like pin and string or floss or something like that to draw with? Okay, don't damage your desks, please. So just use a carpet or cardboard or something like that. That usually works best. So all you got to do is post a photo of what you've drawn and showing your calculations to the assignment, which is on Canvas. And again, let me know if you need help with any of that. But between the video and the written instructions, I'm hoping things will be pretty straightforward. Some of the feedback that I was reading from the comments, and thank you very much for filling all that out, was just including more games or having more things like Kahoots or quizzes or whatever. And so I thought for a ticket to leave today, we'd try doing a Kahoot. It's worked well in my previous classes, so we'll just do that quickly. It's going to be just 4 questions based on the lesson from today. All right. So I know a lot of you probably used Kahoot before, but if not, go to kahoot.it and enter in that code 730-9644. Or if you've got the Kahoot app on your phone, that'd be great. I always advise kids just to use your real name or something close to it. Okay, we got 13 people in class, so let's try to get at least 1 or 2 more in here. Awesome. All right, I'm going to start it, but if you're still trying to join, the code is still in like I think the bottom left of the screen at all times. So, all right, let's go for it. Yeah, there's the game pin right there if you need it. Okay, first question, what is tangential velocity? Yes, indeed. It is moving parallel to the Earth's surface, which is what you were exploring with the orbit simulator. All right, in the lead right now is, not sure who that is. Oh, Nadia. All right, let's see.
Here.
The moon orbits Earth at a constant velocity, same speed at all times. True or false? Very good. Again, I know this is previously we've learned about it just maintaining a constant tangential velocity, but hopefully one thing you took away from the PhET is that is actually false. Its velocity changes depending on where Earth is in its rotation. All right, Neil has pulled into the lead. Here we go. Increasing the mass of a planet could cause satellites orbiting it to Very good. Orbit a bit closer. And again, we saw that in both the do now and in the main activity with the orbit simulators. All right, Neil, but Hank is also on fire, close behind. Last question. What is eccentricity, which we just talked about? Yes, all right, it measures how round an ellipse is, or in other words, how close to a circle it is, right? Remember, they have a score of 0. All right, third place. Nicely done, Neil. All right, goofy stuff. But all right, looks like we're feeling good on that. All right, kids, thank you very much. Your only homework is to complete anything you didn't finish in class today. So make sure that you have answered those quiz questions, posted the Flipgrid video of your screen, and just make your drawings and take a picture. That's all you have to do for Wednesday. Thank you very much. Have a good day. I'll hang out here if you have any other questions or concerns.
Thank you.